We do have an observer in class today, Hunter, who is a prospective student visiting. So, we left off in talking about XV6 file system 2 weeks ago, in fact. So we'll have to try and kind of remember that. I hope you guys all had a good break. I'm glad that it's gotten warm again here, so that's nice. So we looked at how XV6 creates a file. Let's look now at what happens when we actually write into a file. So we'll just echo, I'm not going to use foo because I want something smaller, so we'll just actually echo A into, confusingly, a file called A. So what happens is, first off we write, so if we remember, let's go back and look at how XV6 organizes. So you remember here, the first block is unused, so that allows you to use a drive as a boot drive, and the BIOS wants the boot block as the first, as the block, so we don't want to use it for the file system. So one is our super block that contains information about these other areas. The transactions is actually what we're going to talk about today, once we finish up what we last talked about. And then here we have our inodes. So 32 to 57 packed into blocks, where each inode is, what was it, 64 bytes? 12. Yeah, I think 64 bytes, right? So basically 12 direct block numbers, 1 singly indirect block number, and some flags information, ref counts and things like that. We have a single block in use bitmap, right, where each bit corresponds to one of these blocks, telling whether it's in use or not in use. So if we go back to this slide here, 58 is that bitmap. Okay, so we need to write that to disk to show that we've now allocated a block. Which block have we allocated? 640, because 640 is the one we're about to write to here. So 640 is the one that was written to. We zero it out first, right? We don't want to be left over with whatever happened to be in that block, like let's say an old password file or something. And then we write an A. Why do we write an A? Don't we have a new line here? Right? I think we even looked at if you do an echo by itself, what is it? You don't get a new line, but if you echo something, you do get a new line. And so where's the new line here? Why is it in our write call? So the code will look something like printf 1 and the equivalent of a new line. And yet, we're just going to get a write for the A. And the reason for that is XV6 has its write routine is pretty dumb in that its printf is pretty dumb in that it breaks it down into just calling write once per character. Okay, so not a fast thing, as we know. System calls are not fast, so one wouldn't want to do that. One would want to buffer, but printf doesn't. So printf prints each character at a time. So we get a write, and it's going to now write an A as the first byte of this new block. And the rest of the bytes are going to be 0, because of the B 0. Yeah. Then we got to update the size. Where do we update the size? Where's the size kept for a file? In the inode, right? And also the addresses. What addresses are we talking about here? It's going to be this 640, right? It's basically in our inode. We are going to have, size equals 1, ref count or link count equals 1, and then our addresses, we're going to have 640, and then a bunch of zeros. And then we get our next system call, which has to write a new line. And we've now got to go, what do I actually mean here? We're writing a new line, but writing a new line to the second byte of the file, right? And so therefore, it's got to traverse, find where is that second byte, what block's it in. It's in the first block. It's in block 640. If we go look at block 640, what's in block 640? It contains an A and a bunch of zeros, right? So it'll then go to this block. It'll read it. I hope it doesn't have to read it from disk, because that'd be slow. So let's hope there's some caching, and in fact, we'll see some caching in a moment. So this will actually still be in memory, thank goodness. We write our new line, and then we write that to disk. And then go update the inode. Oh, we're now too big. Do we have to update the address block here? No, because we're just still using the same block here, Brett.
How come it's write a new line? How come it's not just write?
It really is write new line. From the point of view of the block, it's writing a new line and 510 zeros.
So from the point of view, from its point of view, is it overwriting the A that's
Yeah, it's actually not, no. So what it actually is doing is the write call is getting a new line. It knows its offset is 1. It's going to go read this block that says A, and then go pop in a little new line here. So it's, but once we have the block, it's an A and a new line, right? Because it is a block-oriented device. We don't just get to write single bytes to the disk. Okay. Block 58. Block 58 was the bitmap. And so we can see for the bitmap, and you guys had a homework where you worked on this, right? Going through and figuring out which address based on the block number, right? So if the block number, that is the logical block number within the file, is 12 or less, is it 12? Yeah, 11 or less, then it'll be less than the number of direct entries, and we just go ahead and grab the address from there. And if not, we have to go to the indirect block. And if we were using double indirect blocks, we might have to go double. Okay. And then for our allocation routine, we're basically just going to be reading the bitmap block and then going through byte by byte and figuring out where do we actually have a free one available. Right? And then once we find a free one, we're going to mark it in use. So therefore, the bits are free or in use. Does a 1 mean in use or a 1 mean it's free? In use, because here, marking it in use and we're ORing it in. Yep, so. And so what we do then is we're writing to the bitmap block, we release it, and then we go ahead and find this block number and zero out and return that as the block number that we're going to be newly allocating. 640, again, a new line, a bunch of zeros. We have 2 calls to write because we have 2 write system calls because printf is stupid in our user library. It could be smarter because the write system call does take an address, right, and a length. So it could make 1 call instead of 2. Because of the 2 write system calls, the size of the file is first becoming 1 and then becoming 2, and so therefore we have to write the inode twice as well. For deleting, right, there's a couple of things that we need to do. When we delete a file, it's definitely gone from the directory it's in, right? That's clear. So we're going to clear the directory entry of the file of the directory it's in. We have to reduce the number of links in the inode, and then if the number of links is down to 0, then we're actually going to go ahead and mark the block as free. right? If the number of links is greater than 0, that means there's still other hard links referring to this data, and so we leave the inode alone. Okay. Right, we update the inode, setting its size to 0, its address to 0, and then we actually mark it as not valid. Why we do that separately, I think it just has to do with how the stuff is organized. I mentioned the fact that it'd be a real shame if we had to, when we're updating a file, go ahead and read the block from disk if we had just recently written it. And so therefore we have this block cache. So in memory, we keep this cache of blocks. We have a lock that's protecting it. And we have basically this linked list. Okay? And we keep this linked list in order of most recently used. Why would we want to do that?
Most recently
David.
used might also mean like most likely to be accessed.
Yes, so most recently used is our proxy for most likely to be used in the future. Most likely to be used soonest in the future, right? If we actually knew optimally which was the next to be used in the future, that's the one we would not throw away, and we would keep, the one that was going to be used furthest in the future is the one that we would evict from the cache if we ran out of memory. All right. So we have this cache, and the file system goes ahead and calls bget, and bget will make sure nothing else is using this cache, and then go through and just try to find is this block number used. Okay. And we have a reference count to specify how many people are actually using this block. So it's pretty straightforward. So this is the case. Let's just look at here. This is the case where we find our item in the cache. Okay, so we find it, we increment the reference count, we return. If, the little ellipses here, if we don't find it in the cache, then what do we want to do? Well, we want to put it in the cache. So we need to go through and get rid of some block that is in the cache. And so we're going to go through first finding a block whose reference count is 0. Because if we've got a block that's already in use, we want to leave it there. Okay? So if it's 0 and it is not dirty, then we are going to basically reuse it. Okay? We will talk about the dirty flag as we talk about the log today. Okay? The dirty flag basically just says it's been modified, and so it needs to be written to disk. But one has to be careful. We will see when we get into logging that we're careful of when we write to disk, because we want to make sure we have consistency, that we don't just write some blocks to disk and leave other blocks in memory, and then if we crash, we've kind of got some stuff there and some stuff that's not there, and we all hope it turns out well, because it doesn't turn out well. Questions? Okay, and just for locking, we have a lock for the cache overall when one is looking through the cache to try and find out what's there or cache something new. And then we have a lock per buffer to make sure that only one thread is operating on a buffer at a given time. Okay. We talked about this block cache replacement policy. Basically what happens is, right, we've got this bget and brelease pair. So bget to get a block that will then be cached, and brelease to say I'm done with it. And brelease, when it's called, will go ahead and update this most recently used. So it'll put the block you just released at the front of the cache. And it's worth looking at this ordering here. If multiple processes need to read the disk, it's just first come, first serve. Okay? There are a variety of different others that one could use, but this is first in, first out. All right, so today we're going to talk about crash recovery and logging, but before we do that, let's talk about projects. So Lab 4A, I graded that, and you should all have that. Lab 4B, you turned in, you went on break, you didn't think about it anymore. I unfortunately didn't think about it either. So I haven't started grading that, but I will work on that. And then there are 3 more labs. There's Lab 4C, due this Thursday. There's Lab 5, which has to do with file system and I don't remember what else, file system. And then there's the final lab. Okay, so the final lab is one of 2 things. Either you just choose Project 6, which is JOS networking. Okay, so you're going to be adding a Ethernet driver and some networking calls. Much of it will be given to you, but that's basically what you're doing. And you work on that on your own, just like you worked on all the previous labs. That's one possibility. The other possibility is, if you look at Lab 7, there's a bunch of suggestions of what you might want to work on. And you can work on this in groups of 1, 2, or 3. Okay? You just need to get my okay of whatever it is you're choosing so that it has, you know, appropriate scope and relevance. The timing on this is, well, however you want to work to figure out what you want to do together is fine. If you want to post on Piazza, that's fine, and I can give you some feedback there if you'd like. But in any case, April 4th, which is next week, your proposals are due. So your proposal is very simple. I'm going to work on Lab 6, or I'm going to work on this particular topic, you know, a couple sentences, a paragraph of what you're going to do, with whom. Okay, and then I'll give you back as quickly as possible, yes or no on that. And we can revise it to turn it into a yes. Questions on that?
Wait, so do we do the Piazza thing? Is that like the proposal or just
the final proposal is just,
what I want?
What day is April 4th? Does anyone know? Thursday? All right, well, you'll mail me then, I guess, that. And I'll get back to you within the next day.
Discussion due, that's not actually.
There's not really a due. Due is not it. It's like, don't wait until April 3rd to start looking is really what I mean.
But the only thing we need to turn in is what our.
Yeah, the only thing you turn in is your proposal. Okay? And then you basically got a month. If you want to turn in a proposal before that and get my okay, because you have some extra time to work on the lab, then feel free. But the code repository, and you'll need just a brief write-up, like half a page, something like that, describing what you did. And that'll be due May 2nd. And then we'll go over that in person. May 3rd or May 6th. I don't remember the days here. I think it's a Friday or a Monday.
That's only if you do Lab 7, right? You go over, or you can go over in person if you do Lab 6.
Yeah, we'll probably go over in person. Yeah, we will go over in person too. Lab 6. Any questions?
Do
Go ahead,
Lab
Kathy.
6, can you do it like concurrently with Lab 5, or is it kind of like you have to have Lab 6?
Same deal. You got to finish Lab 5 to get to Lab 6. So, and you got to finish Lab 4C to get to Lab 5. All right. So crash recovery. Here's the problem. A crash occurs, right? The power goes out. You don't have an uninterruptible power supply. And so you stop executing code. And you have this cache of buffers in memory, of your disk blocks, and you're kind of left with whatever is on disk. Whatever actual disk operation was issued should be finished. So we can kind of guarantee that if we ask the disk drive to go do this thing, that it will either not do it at all or it'll complete it. Okay? And if it returns and says it is done, then it should be done. Okay? And I talked about the fact that many drives use the rotational energy to basically provide the last gasp of work to be able to write it even without power. So what if you were in the middle of, let's say, writing to a file? Okay? What goes wrong? Well, let's say we're writing hello world all in one call. Okay, so we're writing hello world, we write it to disk, and it's a new file, even, let's say. So let's kind of look through the operations that happen in writing that new file. We've got to allocate an inode. We've got to allocate a data block, which means updating the bitmap. We've got to write to that data block. We've got to update the inode to update the size and that new block number. What else do we have to update for this brand new file?
The free map.
That was like this one, I think. What else do we have to update? The directory entry. Right, we've got to update the directory entry. So we've got to update all 5 of those things. And if we don't update all 5 of them, we have potential inconsistency. So if we update only 3 of them, then maybe we've got a file there, and maybe the in-block bitmap is correct, but we don't have a directory entry, let's say. Okay? And if we don't have a directory entry, what we've got is an orphaned file. Right? It's in use, in the block in use, so we'll never free it, but we don't have any way to get there. So 2 main approaches. The old school Unix approach was file system check on boot. Okay, anyone know what the file system check command is called? FSEK, or FSCK, that's what I was called. So they had to pay by the number of characters or vowels they used, I think. So FSCK is what you use. And so basically what you do when you booted up your system, it'd automatically run, or you'd run by hand, FSCK. Okay? And one of the things it would look at, for instance, is, are there any inodes out there that have no references to them? The situation we just talked about, where we've got this orphaned file. And if so, then it would put it back in the free list. So put its data blocks back as available, and put the inode back as available. As disk drives got larger and larger, that got to be slower and slower, right? Because it's linear with respect to this, roughly the disk drive size, right? The number of files, the number of directories, the number of data blocks, and so on. And so it got to be where that would take hours. So if you crash, right? If you lose power, there's a power blip, let's say, and it goes off and comes back on, and then we'll wait 2 or 3 hours to check the file system before we actually get to use it. So that was considered not so fun. And so another solution, and the solution we're going to look at, is logging. So you're writing file system, power fails, you reboot, is your file system still usable? The case I described to you where we have an orphan file, not so bad. We just have a slightly smaller hard drive now, right? This is kind of one way to look at it. We have a little less capacity. But there are much worse things that can happen, right? Imagine the order that we did stuff was somewhat different. Let's say we wrote our directory entry first that referred to this inode, and we didn't do anything else. So we didn't mark that inode as in use. Well, then all of a sudden we've got a big problem, right? If that inode gets used for something else, then we now got a directory entry pointing to this file that isn't the right file. If we have a data block that got allocated, so we allocated our data block, we wrote hello world, but we failed to update the size, not so bad, right, in the inode. So we think that the file is only 0 bytes big, let's say, and we actually had written 10 bytes, and we lost those 10 bytes. It's maybe not good for that file, but it's fine for the whole structure of the file system. But having directory entries pointing nowhere, having data blocks that an inode points to, but that the bit block says is free, imagine that as bad, right? Imagine you then go reallocate that, and now your data of your file changed out from under you. Or imagine that block was a directory, and now you're writing, you know, a.out to it or something, or vice versa. So there can be bad things that happen. And it all has to do with multi-step operations. If all we were doing was writing a single block, our disk drive guarantees us that's atomic. Writing a single sector actually is. I think we talked about the fact that we sometimes make disk block size or block sizes for the file system multiples of sector sizes. And in that case, we can have some issues if we have a multiple block, but we're only guaranteed a single sector is going to work. Okay. So if you crash, the real problem is your file system invariance may be violated. Like any block that's marked as free isn't in use. It seems like a good policy in general, right? Okay, but if that's broken, not so good. So you can imagine you might have a crash in your file system, you reboot, and if you don't do anything special, there's no file system check, and there's no log to prevent this problem, that you could just crash again because you panic because a block is in use that's not supposed to be in use, for example. Or maybe it doesn't crash. Right? Crashing is not the worst thing to happen. Sometimes not crashing is the worst thing that can happen. Right? You not crash, and then later and later in time, something worse happens, and it was so far removed that you can't even figure out why it was. So crash early, crash often is sometimes a good plan. Okay. And yeah, if you read and write incorrect data, it's like this is a persistent store, and it's not very persistent if it just kind of mutates out from under you. So we do a create, we talked about this. The new directory entry, the file node. We might have a directory entry pointing to the free inode, and that's really bad. If the inode is allocated for something else, oh my gosh, that wouldn't be good at all. If the inode isn't free, so isn't marked as free, but it's actually not used, there's no directory entry that points to it, that's not so bad. We just leaked an inode. Right? But as things go, not so bad. If we do a write, right, we've got to write the block numbers and the length. We might have to write an indirect block, yeah.
So let's say you crash and then something with the file system is not fully updated. So when it when you restart, you realize, oh, there's some problem. So you crash again. Then is there no way to ever...
Well, then what you're going to have to do, so let's say you crash again, you're going to have to say, my file system is broken. I better figure out what's wrong with it. I better write myself a little utility to go through and read through and check all the consistency and verify it is, and you've written FSEK, which we'll go through and fix it. Right. So, does that answer your question? Yeah. Okay. You're having to write the content of your block or blocks, the block-free bitmap. And so again, your inode could refer to a free block, right? Very, very bad. Again, this is your file changes, content changes out from under you. Or block not free but not used. We just, again, leaked the block. Not so bad. Unlink. Again, the key here in all these is we're writing multiple blocks as part of a single, think of it as a transaction, or in this case, a system call. So we've got block-free bitmaps. How many blocks might an unlink be freeing?
The entire data part of the file system minus whatever's required for like the root directory and stuff?
I think no. So not quite the entire data blocks in the file system. It's only one file that we're unlinking, right? And so that one file can comprise how many blocks? It was on the exam, yeah, so you should all remember it. It's, right, we had one indirect block, which could hold 128, plus another 12 direct ones, so that's 140 blocks. So here, since we only support small files, it's not so bad. At most 140 blocks, which means at most 140 bits in the block-free bitmap. Right? But a larger file system, in our case, we only have one block of bitmap, but we could have multiple blocks of bitmap, so we could hit a lot of these. And we've also got to erase the directory entry and free the inode. Okay, and again, bad things can happen. So we reboot, we run our recovery code, right? We run our FSCK. And we're going to then make sure our invariants are maintained. So there's nothing that's both in use and free. Okay? That's easy enough to verify. Although we've got to scan probably, we don't have to scan the entire disk. What part of the disk do we not have to scan? Or rather, let's look at what part of the disk we do have to scan. So we need to scan. Do we need to scan inodes? Yes, because we need to check and see which ones say they're in use, which ones say they're free, and also which blocks do they refer to. Do we need to scan the bitmap free block? Yeah, because we need to see, does it agree with the inodes, right? As to what they're the real truth, I guess, of what is in use, right? Do we need to scan the contents of data files?
Does that include directory entries?
Well, so that's why I said data files as opposed to directory files. So why don't you answer the directory files? So yes, we need to do here, and that's a good point. Those are also blocks in the data. So contents of data files, no. Directory files, yes, because we basically need to match up the directory entries to the inodes and make sure we don't have any either directory entries that point to free inodes, right, or inodes that no directory entry, inodes that are not free that no directory entry points to. We've also got to check the indirect data blocks.
Check reference counts of inodes.
Reference counts of inodes as well. So no loops. Is that disallowed?
Like, what if you have two directories that both have each other in them but aren't referenced anywhere from the root directory?
Oh, yeah. Certainly, you need to make sure that you're starting at the root directory, and everything needs to be accessible from the root directory. Yeah, that's a good point.
Directory reference loops are bad. I guess they
Yeah,
could be.
yeah. And then, yeah, we do need to do our count of our inodes to make sure that the number of directory entries that refer to the inode matches the count of links in. Does that make sense? So one could write such a thing, and it'd be boring and ugly, but yeah.
So this would not allow you to recover if the inode the size was wrong.
If the size was wrong, we couldn't recover that. Well, so we'd have to do a little bit of something. So let's say the size says that it's 0 big, and we have 100 blocks allocated for it. We need to pick one or the other of either says the size, and I don't know exactly how big you'd make it, right? We could have integral for all the first blocks, but I don't know what to do with the last one. Or we just say the size is 0. And part of what we're going to do is we're going to create a log as we're writing our FSCK. And we might have some exclamations in some cases. This one might be such an exclamation. We've got, 50,000 bytes for this file allocated to it, but we think the size is 0. And you could even, write down the block numbers so that someone could then stop, not use the file system yet, and go and try and recover. Does that make sense? All but the last few operations are on disk. Okay? The last few operations, so this is what you'd like. The last few system calls you made, so from the point of a user, the system calls you made up until the last few, they're there on disk. Again, it's part of this persistent store we have is persistent means even if it crashes, it's still there, modulo the last little bit. And what that last little bit is it may be a trade-off there between how small you want that versus how fast you want things to run. Okay, So if it's yesterday, you definitely want it there. If it's stuff that was in the 60 nanoseconds before the crash happened, you don't expect it. And in between is a gray area. And you don't also want any order anomalies. For instance, if I echo 99 into result and then echo done into status, I want to make sure that status doesn't say done while there's no result file, for example. This happened before this, so I want that consistency, that either this happened or both of them happened, but not just this one. Does that make sense? All right. So, if only disk writes weren't slow, this would be much less of a problem. But disk writes are very slow, and so we try to avoid writing to disk, and that avoiding writing to disk is what causes these issues. Part of what causes the issues. So, safety says, write to disk as soon as you possibly can. Speed says, hold off writing to disk as long as you possibly can. Okay? You might batch things, right? So you're writing multiple blocks at a time, which can allow the disk drive to have higher throughput. You might have a write-back cache, and that's what we're going to actually look at. So a write-back cache, you write to the cache, and the cache is just in memory, and it doesn't write to the disk immediately, and later on, it'll write it back from the cache to the disk. That's the approach we're going to be using. There's sorting that can happen, so if you're writing multiple blocks, I think I talked briefly about this, that you may want to order which tracks you're writing to, and disk drives actually often will do that automatically. You say to write these particular blocks in this order, and it will rearrange them to do it quicker. Okay, so you got to kind of take that into account as potential problem. So this crash recovery, I mean, it's not just file systems. It's any place we have some sort of persistent storage. Databases are a great example, where databases, again, you're running a database, you're issuing transactions and operations, and if it crashes, you want it to come back up and either have, if you committed a transaction, it completed, and if you didn't, it doesn't show up there, and no partial effects are there. It's all or nothing. All right, so logging, also called journaling. The goal is atomic system calls with respect to crashes. We're going to see this is not going to be 100% true here, but basically we do a system call, like for instance, create or write or unlink, and it either entirely happens or doesn't happen at all. Right? But there's none of this half there, half not there. And we'd like fast recovery. We don't have an hour long is actually underestimating, no multi-hour long. Okay, FSC case. So we're going to look at two different things. Today we're going to look at XV6 and how XV6 does logging. And then on Wednesday we're going to look at Linux at the ext3 file system, which was basically just an existing file system, ext2, with logging on top of that. Okay. So XV6 provides a lot of safety, and the recovery's fast. It just doesn't happen to have a lot of throughput. It's kind of pokey. And Linux is a little more complicated, but faster. Oh, and I should also point out, starting with Wednesday, your readings are going to include or will be actually papers. So we're no longer going to be reading from the XV6 book. We're going to just be reading papers. To begin with, we're going to be reading a paper on Linux ext3. Starting next week, and I'll talk about this more on Wednesday, you're going to actually, your homework will be to submit a short response about the paper. So there'll be a question about the paper, and part of what you'll also do is supply your own question. So things that you had question about in the paper, and that'll help me guide the lecture. I'll talk about that more on Wednesday. All right, so you want atomicity. No quarks, right? We're classical atoms. We'll call it a transaction. Okay? So in transactions, so for databases, for instance, how many people have worked with databases? All right, so for transactions, you can do things like begin a transaction and then do things in multiple tables, for example, and then commit the transaction. And then you're guaranteed that all those things will happen. You can also abort a transaction. You can say, oh, I was doing this, I wanted to write this to this table, this table, and I just decided I don't like that. So undo these steps that have been partially done. We don't have to worry about aborting. So we know we're doing a system call, we want to carry out this operation, and so we just have to support committing. So we're going to begin a transaction, and then we're done, we're going to commit. And the key thing about a commit is it's, I think it's sort of like, you guys ever been to the Rockies? Right? If you go up in the Rockies somewhere like, for instance, in Colorado, for example, right, we have the Continental Divide. And there's a little plaque there, and you can stand with 1 foot on one side and 1 foot on the other. What does Continental Divide mean? I mean, it divides the continent, but yeah, go ahead.
One side, the rivers flow one way.
If you spit on one side, right, it will eventually flow towards, I was thinking, can it really be the Atlantic? I mean, or the Gulf of Mexico, or that way. And then on the other side, the rivers all flow the other way, okay? And that's kind of what it is. There's this cusp where on one side one thing happens, and on the other side a totally different thing happens. And that's what the committing is sort of like. So we begin our transaction, we do our thing, and then we get to the commit. And the commit, we either fail totally and fall back into the ocean here and nothing happened, or we fall this way and everything worked. So it's completely all or nothing. And the way we do that, we're going to have a log on disk. It's got to be on disk, because if we lose memory, we don't have the memory anymore. So we have a place on disk where the system call is going to record all the writes that would happen and where they would go. All right? So far, if we're going to fail here, we're going to fail back this way, right? Because we won't actually ever do them. And then, when we're done with all the writes that we would do, we write the equivalent of done. And done says, that's all the writing we're going to do for the system call. After the done is there, then we're going to actually do the writes in the right place. So, we're going to copy basically our blocks from the log to where it belongs. The next block from the log to where it belongs. And keep going until we've got all of them on our actual file system. And then we don't need the log anymore. Okay? And so then we'll, and this doesn't quite say it, but we'll then clear the done. All right, so if we didn't have any crash, that's fine. It seems like extra work because we wrote to the disk and then we wrote to the disk again. But if we do have a crash, we look at the log and we see, is there a done there? If there's not a done there, don't do anything. Just fall back to the left, ignore the stuff in the log. It's not going to the file system. It's as if that system call didn't happen. If there was a done, we're going to replay all the writes. Now, some of the writes might have already completed, right? Because we were writing here. We were going in and copying every block from the log to the file system. This would just do it again. And we can convince ourselves that that's not going to hurt us to rewrite a block as long as it's the same contents. Okay, to do it over again. So we rewrite over again. Once we've written them all, replay all the writes in the log, and clear done. So if we crash before the done, we know what happens. We just ignore it. If we crash after the done, but before any of the disk writes, then this crash recovery is going to copy all of the disk blocks. If we crash in the middle of these disk writes, then it's going to copy some that are already there and continue copying the rest. and then finish. And if it crashes in here, again, so we have 2 crashes. We crash once, let's say after the done, and then it's a flaky power supply, right, or something else, or flaky power. And then we crash again as we're copying. Well, when we come back up again, we'll look. Done is there. We're going to try copying again until we can successfully get through this and clear the done. Yeah.
Why do we just clear the done and not the whole log?
We could clear the whole log. The done is our single. So what we have to make sure of is our decision of whether we need to recover or not is limited to a single sector on disk, because that's the only one we can guarantee will be written atomically. So we may go ahead and write done and then update some other stuff in the log, and we'll see we don't actually really write the characters done. We're going to do something slightly different. We're going to just have a count of how many blocks are in the log. This is what we'll use. So we'll set it to 0. And so that effectively clears out everything else. Other questions? All right. So we are not going to write any of the writes that should go to the file system until we've got them all in the log, because that's the only way we can guarantee we'll be able to replay them in case a crash happens. Okay? So they're all in the log before we start putting any of them in the file system. So the key is every write in the log, then commit, then every write to the file system. And this has to be atomic, that commit. And it will be as long as we write one sector. Does that make sense? Okay. So, as soon as we write anything to the file system, we have to write everything else. Since we have to write everything else, we have to have everything else saved for us. And the only way we can do that, given that there may be a crash, is write it to the log. So it has to be on the disk, although not in the file system. Right? We're keeping the log someplace special. So the other writes have to be there. Where are they? They're in the log. Logging actually works really well. So logging can work without knowing anything about the underlying file system. You can basically take an existing file system and add logging to it. Right? The file system will have to make logging calls, like say kind of the equivalent of a begin transaction, commit. But it can operate on top of it, basically. And that's what the ext3 file system is. In fact, the only reason, as you'll see, I don't think the paper describes it, but ext3 file system is the ext2 file system with logging added on. The only reason it's a separate file system is because the guy who was working on it didn't want to be running his new stuff on his root file system, which I think makes sense. So, and it can also be high performance. All right, couple things one has to be careful of. So a system call can update a cache block, right? Any block you're going to be operating on, in fact, is going to be in the cache. If it's already in the cache, that's okay. It can change it. If it wasn't in the cache, it'll have to be read from disk, and it can be changed as well. That's fine. But again, we can't write it back. So therefore, the cache better not, behind our backs, try and write blocks to the file system. Right? If the cache runs out of space, we saw it's going to just go find someone to evict, and it will though evict. And so the rule that we use in XV6 is the cache can't evict dirty blocks. And so what we're going to do then is anytime we are writing to a block, we're in this transaction, we're writing to a block, we mark it as dirty, and we're going to be responsible, the logging system, for getting it to disk. We do not rely on the cache for getting it to disk. So for example, when we do a create, we create an inode, right? That is, we take a free inode and we use it. We're going to write that to the log. We write the directory block, the directory entry, the block containing the directory entry to the log. If the dirty inode were evicted here, we have a big problem. Right? Because if the dirty inode were written to disk before we committed, then if we crash before the commit, the inode has been updated, but the directory entry hasn't. So therefore, we can't have this eviction here. So part of what that means is the cache has to be big enough. Right? If the cache were too small, we wouldn't be able to hold this in memory and do everything we need to do. So the cache needs to be big enough to hold all of the blocks that a transaction might need. So what's the system call that would dirty the most number of blocks? That would write to the most number of blocks? I mentioned remove, unlink, as a possibility, right? Because it could write to a lot of bitmap blocks because it might free a lot of blocks. But there's a worse one than that. Rename is a handful. I'm thinking of one that could be tens or hundreds of blocks. Copy is not a system call. But to implement copy, what does one do?
Create, read, write.
Create, read, write. Create, not so bad. Read, not so bad, because read doesn't dirty anything. Write, how big a write can you do? As big as you want.
Up to the size of a file.
There's nothing preventing you from doing a larger write. It wouldn't, yeah, you get an error, but yeah. So a write can be unlimited size. And so therefore, it's an unlimited number of blocks you could be writing, ignoring the fact that files have a maximum number of blocks they could be. Let's say we supported doubly and triply indirect blocks. So the buffer cache might have to be big enough to hold all of them of this potentially unlimited size. That's a problem. And so therefore, we have a specific solution for write. And that is, we take advantage of a nice feature of write, which is if you ask to write 100,000 bytes, it might return 1,000, saying, oh, I wrote 1,000 of them for you. Okay. So what we actually do is just break up the write into multiple transactions. So we'll have one transaction with the first X many bytes, and another transaction with the next X many bytes, and so on. So what the effect will be is when you do a recover, maybe part of the write succeeded, a prefix of the write succeeded, but not necessarily the entire write.
Why do we need to journal data blocks?
So why do we need journal data blocks? Data blocks do contain directory entries and indirect blocks. The simplest answer, though, is it's simpler if we do all of it. So XV6 is going to do all of it. We will see that Linux has the ability to just journal the metadata. Okay. So the nice thing about journaling if you journal just the metadata, you're guaranteed you'll have a consistent file system. The problem might be your data might not be 100% in line. The way we're going to do it here, where we're going to journal every block, is going to ensure that both our metadata is correct and also the contents of our files completely matches this system call interface. So let's look at what we got here. We've got in memory we've got a cache. So this is our buffer cache. Okay. What else do we have in memory? We have our log information in memory. So this is our log info. Our log info consists of the number of blocks that we've logged plus block number 1 all the way to block number n. Okay. So this is going to just be where this block is going to go. So there's a block associated with this. Like let's say we have right now a 1 for the number of blocks. And we have 762 as a block number. That 762 refers, let's say, to this. This is cached block 762. So that means the contents of this should be eventually written to 762 on disk, to the file system 762. But we're just keeping this in memory for right now. Okay, so as we go through, we're accumulating all of the writes that are going to happen, and we're going to be updating this log in memory for the moment. We will have to get it to disk at some point. Okay. And then we have our disk. Right, disks are typically represented like this because they used to be big washing machine type things. So this is on disk. And on disk, we have something fairly similar to the log info. So we have log, a log header, which contains the same information. The number of blocks, the first block number, the second block number, however many blocks we say. So if we're going to match this, this would be 762. And then after this, after our first header, we have a bunch of blocks. And this would be, this first one would be the contents. Let's say for 762, right? It's going to be this right here. Whatever the contents were here, once we've written it out to disk, that's going to be here. And our header says the contents here belongs at 762, right? This is not block 762 right now. This is wherever we are on the log, 35 or something. And this is 36, and this is 34. And then we've also got the file system. So separate from this, but on disk, we have the file system. So there's a blocks for the inode, blocks for the bitmap. It's basically all the blocks that are not for the log. And we don't touch this. We touch the log. So on every write, we're of course writing to the buffer cache. We're writing data to these blocks. These might be bitmap free. This might be inodes. This might be directory entries. This might be hello world stuff, right, in a.out. And we're updating the log. Okay, we've got this block we just wrote to. It's this block number. We got this block we wrote to. It's this block number, and so on. And then when we get a commit, right, that is when we say the transaction is over, we're done with our writing, then we're going to write the buffers to the log on disk. So these buffers, read the blocks from the cache, write them to disk here. Okay. We wait. We say, disk, let me know when you're finished. The disk says, we're finished. And then we trust that the stuff is actually written to the disk. And then we write the header to the disk. It's important that we first write the blocks and then write the header, because it's the header that's actually got kind of the done in it. Because the done is, how many blocks do we have? If it's non-zero, That means we're done. And then after the commit, we install, it's called installing, all these blocks one by one to the appropriate location on disk. Okay. And I say one by one, we actually will just issue commands to the disk as fast as we can, and if it can accumulate those and optimize that, that's great. And then once we're done with that, we go back and write 0 to here. Does that make sense? That's going to work. Okay. So the N is the commit. 0 means it's uncommitted. There's no recovery necessary. The non-zero means it's committed, and you have to copy the stuff from the log to the disk. And we don't know how much of it you have to copy, so copy all of it. And it's the point you do that right that's when the commit happens. And actually, I guess, really, officially, it's when the write makes it to disk. Okay? But the good news is it either makes it or it doesn't make it. You either fall one way or the other way off the Continental Divide. We talked about the fact that the writes must fit in the log. And so since the writes are sort of unbounded, we just figure out how many. We basically want to find, for every system call, what's the maximum number of blocks it can touch. And we want to make sure the log size is at least as big as that. Writes are a special issue, so we're going to break those up into multiple transactions. Okay.
How do we parallelize this log? Like, what if we have multiple transactions that want to write to the same block?
So let's look at that. Let's say we had concurrent system calls. What would happen? Okay, here's one possibility we could do. We could say we're going to allow only one system call running at a time. That seems extreme. Another possibility is we could say we're going to only allow one call that writes to the file system at a time. So that would be smaller, right? Reads would be allowed in conjunction with other stuff. But for performance, we really want to support multiple system calls. Okay? It must be different processes, right? So with respect to a single process, when it makes one system call, that's one transaction, and that's done. And when it makes another system call, that's another transaction. So what we want to do is we want multiple system calls to be in the log. How many? Do we have to come up with a limit? Or could we have an unlimited number? There's a limit to the size of the log. We know that the maximum size any system call can write, the log is at least as big as that. So we probably will have the maximum size any system call can be times the maximum number of concurrent transactions we might allow and make sure our log is that big. All right? So we might allow 3 concurrent file system write transactions to happen at once. And they'll just all share the log. That's what will happen there. But a single commit has to write them all. So let's just actually kind of look at this. So we've got, let's say, 3 processes, 4 processes, P1, P2, P3, and P4. And this one does a system call that has this kind of duration, where it's starting something, it does a bunch of writes, and it finishes. In P2, let's say, looks like this. In P3, looks like this. In P4, looks like this. So if they continue to be, so here's the problem. We want to have a single commit that's going to write the transactions for multiple system calls. But we don't want to write data from a call that's still in the middle, right? Because it might crash before it has a chance to write more stuff, and it needs everything to be at once. So we have to wait until the transaction is over. So that means, although this might be what the processors are trying to do, that's not what's going to actually happen. Let's say we support 3 concurrent system calls. We're going to delay this guy And we're going to say, hey, you're the fourth system call. We only support 3 system calls. You are going to sleep, and we're going to wait until all 3 of these finish. And then once all 3 of these finish, we'll go ahead and commit. And once that commit's finished, then we'll go ahead and wake this guy up. Okay? So if we look at our log is going to have the number of blocks, and it's going to have a bunch of blocks. So some blocks are from this transaction. Some other blocks are from this transaction, and some other ones from this transaction. But we just threw them all together in the log. And some, how could it be shared? Is it possible we could have multiple system calls that are writing the same block? If I create a file at the root directory and you create a file in the root directory, we're both creating a file in the root directory, and so we both need directory entries in the root directory, and so therefore we could very well both be writing the same block, right? Now we're not going to write exactly at the same time because the block has a lock on it. So I'll write first, I'll write my thing, you'll go right to that same cached block, and then that block we both get credit for, right? Because we both got to write to it. Does the concept make sense? Or this waiting?
So do multiple system calls end up going into the same transaction? System call its own transaction.
It's a terminology question. So multiple system calls go in the same transaction. So is a transaction what a particular system call writes, or is a transaction the collection of all of them that they write?
I mean, I was thinking of a transaction as whatever our unit of this is atomic.
In our case, our unit of atomicity is all of the system calls together and the changes that they are trying to make to the file system. So they all got batched into a single transaction, yes. So here's the rule. If a new system call comes across that's trying to write to the file system, right, that basically says begin transaction, you check and you see, are we going to be able to fit that in the log? We know how much space is left in the log. We know how many system calls are running and how much they've used so far, or how much they could possibly use. And so we can just do a simple calculation to figure that out. And if it won't fit, don't start it. So basically, you don't start unless you know you can successfully satisfy all the writes that are needed. And then we'll just go to sleep and we'll wait for all the current calls to complete and all of them to commit, and then we'll wake up and we'll go. When the number of in-progress calls falls to 0. So here, when P1 starts, we're going to keep track of the fact that we have 1 open system call running. And this one will have 2 open. And this one, when it wants to start, yes, we still have enough space in the log for you. Even if you wrote your maximum, there are 3 going. When this one finishes, we're down to 2. When this one finishes, we're down to 1. This one finishes, down to 0. Okay, at this point, when we're down to 0, commit. Free up your log space. Commit meaning copy all the stuff back to the file system, and then wake up after you've done all the writing and the installing. Make sense? Okay. A block can be written multiple times in a transaction. The way we're doing writing here is until we get to the commit, we're just operating in memory, right? We're just operating on cached blocks. So it's actually really nice because we're not actually going to disk. We're going and updating this block multiple times, like we might be creating files in a directory. We might be allocating a bunch of blocks, which updates the bits in the bitmap free block. And so there might be these multiple uncommitted transactions or multiple operations within a single system call. And they all get coalesced together and end up as a single write of that block after all those changes have happened. So that's good. So this is what's called write absorption, that we're absorbing these multiple writes, and it turns into just a single write at the end. Does that one make sense? Questions on that? All right, so we've seen this diagram before, and here we're going to be mostly interested in the log, which is going to run from 2 to 31. So let's say we do echo A into X. So first, we're going to have 3 system calls. Create A, write A, and write a new line. And let's assume there are no other processes running. By the way, I said, slightly incorrectly, that from the point of view of a single process, a system calls a transaction, and that will finish. The one transaction will happen before you have the next system call. That's not 100% true. If we had another process running that was doing a long system call, we could come in, be part of its transaction, return, come back in, it's still running, we're part of its transaction, we come in. So we could actually have multiple system calls that all become part of one single transaction. But in any case, we're going to write physical block 3, right? So this is to the log, the first block after the header. And what we're going to be writing is inode number 35. And actually, we're not even writing this to disk yet. The first thing that happens is we write it to memory. But once we've written it to memory and we finish our transaction, then it's going to write it to the log, yes?
Does x86 have a facility for saying, I really actually need this to be written to disk before I keep going?
XV6 doesn't have any sort of a file sync or flush mechanism.
Those things would be for.
Yeah, yeah. Fsync is a good example would be if you got a mail processing program, right? That is, you're writing a mail server that's an SMTP server, I guess it'd be, yes. So it's accepting incoming mail from someone else, and it only wants to respond okay to the person on the other side once it's written the file to disk, okay? Because it wants to know it has the mail and tell the other guy I've got the mail. And so mail systems will often do a sync saying, I want to make sure this file is actually on disk. But we don't have it. So we've got our directory content for X, right, our directory entry. We've got a okay, so we're going to look at what's actually written to disk, right? It was in memory, and we had our inode and our directory content. We don't have any data blocks because it's a zero-size file so far. So we write the inode, write the directory content, and then write the log header. At the point we've written the log header, we are committed. Now we write whatever's in block number 3 here. We know from our log header that it's supposed to go to 35, and so we write it into 35. We do the same thing for here. Number 4 goes into 63. We write that, and then we go back and write 2 again. Are we having to read, by the way, 3 and 4 here? From disk in order to write them out to disk? Not here, because here they're still cached. If we crash and come back up, then yes, we're going to have to read from disk. But really, 99% of the time or higher, 5 nines, we're writing to the log and never reading from that log. Write and write and write and write just in case we might need it, in case we have a crash.
So it seems like we're now writing slightly more than twice as much as we did before.
Yes. Basically, yes.
Isn't that bad for performance?
XV6 is not performant. So, and we got a little more that goes on here, right? When we write A, so we've got our bitmap, because we've got to allocate a new block. We've got the file content, because we're actually writing the A. We've got the inode, because we're updating what?
The size and the block list.
Size and the block number, which is at 533. And then we write the commit. And now we go through and basically write these again to their final resting place, and then go back and mark the log as empty. And I'm not going to show you the new line one. Give me one more minute, and then I will break. So let's look at the second transaction where we're writing the A. So what happens? We're in file write. And file write, if you look at it, actually has a bunch of if statements of different kinds of things that you might be writing to. You might be writing to console or networking. In our case, if you're writing to an inode. We write a few blocks at a time. And what we do is go through and begin an operation, that is, begin a transaction, do a write, writing possibly smaller amount of data than was requested, and then end the operation. And then go back in and begin a new operation, and so on in the operation. Okay? If we look at write, it's going to go through, and remember bmap is the one that will tell you for a given block number it'll tell you for a given logical block number what physical block number it is. So this may have to allocate an indirect block, okay? Which in our case it will. And when we do an I update here, updating the size, this can also write the bitmap. So both of those can be doing that, but we're part of a transaction. And we'll do the rest of this on Wednesday.